You've probably heard the classic story, right? Isaac Newton is sitting under a tree, an apple falls on his head, and boom, the theory of gravity is born. It's this perfect image of human intuition, a sudden flash of genius. We really love to think of scientific discovery as this magical, creative thing that only humans can do. But what if it's not? What if you could actually break it down step by step into a formula? Okay, let's really get into this. And that brings us to the central question we're digging into here. And honestly, it's a pretty wild one. Can we actually teach a machine to have one of those Eureka moments? I mean, can you write an algorithm for a flash of insight, for discovery itself? It's a massive idea. And believe it or not, researchers are tackling it right now. So yeah, this isn't just a late-night philosophical debate anymore. This is a real computational quest. It's an attempt to build a formal model for how we come up with new ideas, how we test them, and how we represent totally new knowledge. It's literally about trying to codify the scientific method. But before an AI can go off and discover the next law of physics, it has to figure out something way more basic. Let's say it generates thousands, maybe millions of possible ideas. How in the world does it know which ones are actually promising and which ones are just junk? It needs a filter, right? A way to evaluate and prioritize what a good idea even looks like. This brings us to the first big strategy. If you want a machine to come up with good hypotheses, you can teach it to look for the simplest, most elegant, most compact explanation for all the data it's seeing. And this whole idea is formalized in something called the minimum description length principle, or MDL. You can just think of it as Occam's razor, but for a computer. The basic idea is that the best theory isn't just the one that's right. It's the one that provides the most compressed, the most elegant explanation that still fits all the facts. It's all about finding that clear signal inside all the noise. So how does it actually work? Well, a scientific theory is basically treated like a computer program that's designed to explain a set of data. Its length is just the size of that program, plus the size of the data after the program has done its job compressing it. The best theory? It's simply the one with the shortest total length. It's a really clever way to computationally measure both elegance and power at the same time. Okay, so you've got a good hypothesis. Great. And now you have to test it. But here's the thing. Not all experiments are created equal. How do you design one that gives you the absolute most information possible without wasting a single bit of effort? This gets us into the idea of smart experiments. And this is where a method called adaptive design optimization, or ADO, enters the picture. And it is a total game changer. The entire point of ADO is to run experiments that are smart. Each step is specifically designed to be maximally informative, to squeeze every last drop of useful information out of the process, which can just dramatically speed up discovery. And you can really see the difference here. Traditional experiments are all planned out ahead of time. They're fixed. But an ADO-powered experiment, it's alive. It adapts in real time based on the data that's coming in. This makes it so much more efficient, letting it figure out which model is best with way less data. All right, now this is where things get really futuristic. So we've talked about how an AI can generate ideas and test them, but what about the spark that drives all of this? What about good old-fashioned curiosity? Is it possible to actually write code that creates an internal drive to learn and to explore? Well, welcome to the active inference framework. It's this incredible model of how the brain might work. And it's all based on one single profound directive: minimize surprise. The idea is that everything we do, from seeing and hearing to learning and acting, it's all driven by this deep fundamental need to make the world around us less surprising, more predictable. And just look at what that one simple rule leads to. To minimize surprise, a system has to figure out the hidden causes of what it's sensing. It has to learn the patterns of its world. And here's the real kicker. To reduce its own uncertainty, it has to actively seek out new things, new information. And that, right there, is a computational model of curiosity. It basically becomes a digital engine that's always testing its own ideas to build a better and better map of reality. So, we have a model for generating ideas, for testing them efficiently, and even a model for curiosity. I mean, it really sounds like we're getting close to cracking the code, right? But is there still something fundamental that's missing? Is there a kind of ghost in the machine that we just can't capture with an algorithm? And this is the big philosophical question, isn't it? Is real scientific discovery just a super sophisticated game of pattern matching and optimization? Or does it need some uniquely human skill that might just be impossible to program? And right here is where we find a really crucial difference. A learning machine, no matter how powerful it is, basically adjusts its internal theory to make sense of the data it's given. But a human scientist, they do something else. They don't just change their theory, they change their tools. They build a new telescope or a new microscope. They fundamentally change the data stream itself to ask completely new kinds of questions. And this skill, this adaptive adjustment of our tools, well, it might just be the secret ingredient. Some people argue that it's a kind of intuitive ability that happens before we even have the words for it, something that you just can't write down in formal code. It's the difference between solving the puzzle you're given and inventing a brand new puzzle. And that might be the one part of discovery a machine can't replicate.
Which leaves us with a pretty fascinating question to think about for the future of science. Will the next great breakthrough, the next Einstein, come from a moment of human insight, or will it be the logical output of an algorithm that was designed to compute discovery itself? Definitely something to chew on.